Assalamualaikum and salam sejahtera. My name is Amisha binti Mahizan, matrix number A175395, and today I will present about digital radiographic technique, which is focused on computed tomography. Next, moving on. Radiographic testing is a non-destructive examination technique that involves the use of either X-rays or the gamma rays to view the internal structure of the component. So RT is often used to inspect machinery such as pressure vessels and valve to detect for flaws. RT is also used to inspect the weld repairs. So by comparing to other non-destructive examination techniques, radiography has several advantages, which is it is highly reproducible, can be used on a variety of materials, and the data gathered can be stored for later analysis. So in industrial digital radiography, they are comprised of three main technologies, which is computed tomography, direct radiography, and computed radiography. So each of these products has their own unique characteristics and challenges. But today, we will focus more on computed tomography. So computed tomography or CT scanning is based on radiographic technology, which provides an ideal testing technique in order to locate and measure volumetric detail in 3D. So the ability of X-ray to penetrate through varying densities allows the CT inspection results to provide a non-destructive physical characterization of the internal features and structures of a part or a component. So industrial CT scanning is able to access internal data equally well on metallic or non-metallic specimen, solid and fibrous materials, and also a smooth and irregularly surfaced objects. So as we can see on the slide, this is the example of the image on how the CT computed tomography operates. So briefly, the tomography works in the following image. The sample or tested object is placed on the mechanical unit, which allows for its translation, rotation, and movement along the z-axis. Following that, the sample is exposed to the collimated beam. Between the source and the detector, the collimators are used to focus the light. A microcontroller equipped personal computer is responsible for the precise motion control and data collecting. Then, an amplifier, a preamplifier, and two channel analyzer are used to process the information gathered by the detector. So, data storage and processing, reconstruction techniques, and the final display of 2D and 3D tomograms are all carried out by specialist software programs operating on the PC. Next, here is the example that can observe by referring to the previous published reports. Next, here is the method that been used in the previous published journal as our reference. So the X-ray tomograms were scanned at a RayScan 250E system with a 225 kV microfocus tube and a 450 kV macro focus tube. So the target material that is used is tungsten for both tubes. The diameter of the X-ray spot for the 225 kV tube is ranged around 5 to 200 micrometer, depending on the selected tube current, and about 2.2 mm for the 450 kV tube. The two different X-ray tubes produce different X-ray spectra, since the geometry, tube current, and energy windows are different. The detector of the device used is a silicon flat panel matrix detector, which is Perkin-Elmer RID 1640 AL1ES with a gathered scintillator. That is the name of the detector. So in figure 1A, as you can see, the huge instruments are the picture of the computed tomography system. The computed tomography has several measurement modes, including radioscopy, 3D CT, and region of interest, or known as ROI-CT, especially for flat parts and flat regions of complex parts. And the next picture of the figure B picture is the figure of principal measurement geometry. Right, so moving on for the workpiece number 1. So this figure, as you can see, shows the 3D CT result, which is focused on cross-sectional images, and the graph below the picture is a gray value profile along the long axis of the aluminium component, which is the workpiece number 1. They are obtained by using the 225 kV and 450 kV tubes. The aluminium part has a rather simple geometry, consisting of a series of steps and a few air pores embedded into the material. So when we comparing the findings obtained by the micro focus tube and the macro focus tube, it is clear that the micro focus tube, which is a 225 kV, provides a significantly more detail due to its better resolution. So the CT results, on the other hand, is a significant result, which is the surface of the part. For example, the interface between aluminium and air is smeared, and the gray value in the part is highly inhomogeneous, despite the fact that the material density is rather constant. So the CT results obtained with the 450 kV tube, on the other hand, show a very bad, not bad, but kind of blur outcome images. The gray values within the material and the air are relatively constant, but the resolution is significantly reduced. So it is kind difficult to differentiate between the details. Moving on to workpiece number 2. So a complex industrial aluminium workpiece from the automotive industry is represented in the following examples of CT results. The CT cross-section of measurements with the 225 kV tube and the 450 kV tube are shown in this figure for comparison. CT data obtained with the 225 kV tube shows a very higher resolution and show more details, but CT result obtained with the 450 kV tube have a very lower resolution and show less artifact, similar to the CT studies performed on the first workpiece, which we can see from the previous slide. So, when comparing the CT results of the workpiece number 1 and the workpiece number 2, it can be clearly see both the measurements with the micro focus tube are generally more suitable for a non-destructive testing defect characterization and detection, and that they are particularly useful when dealing with fine structures and small flows. However, CT measurements with a high energy tube of 450 kV tube are typically more suited for dimension measurements and for obtaining the geometry of the investigated workpiece, since there are fewer artifacts and the surface of the workpiece may be segmented more precisely than with a low energy tube. The last workpiece comparison is workpiece number 3. So an industrial plug made of metallic pins and a polymeric substance that serves as the electrically insulating housing is the subject used for the workpiece number 3. The figure shows the CT results obtained with the 225 kV tube and also the 450 kV tube. So, the CT results obtained with the 225 kV tube show a spectacular artifacts caused by the metallic pin, which may be seen in the images. Because of the strength of these relics, the polymeric material in the vicinity of the material pins cannot be defined or examined using the CT scanning. This is owing to the extremely different attenuation coefficients of copper and polymer, which resulting in a dynamic range of the detector that is greater than the detector's dynamic range. As we can observe on the right hand side in this figure, the CT results obtained with the 450 kV tube are far more better and the artifacts are significantly reduced. Although it is possible to view both the metal and the polymer in the same picture, the polymer is not correctly portrayed due to the absence of certain portions of the housing. Of fact, because the X-ray spot has a diameter of around 2.2 mm, the margins of the CT images produced by the 450 kV tube are much less sharp than they are in the conventional CT images. With the help of the selected local threshold methods, it is possible to extract the geometry of the metallic pins and the polymeric housing from the 450 kV CT. It is not acceptable to use the same technique to compute the geometrical results for the CT measurements taken with a 225 kV tube, since the geometrical results are not satisfactory. So, to be summarized from the comparison of the 3 different workpieces that I shown before, when different X-ray sources and CT measurement modes are combined within a single CT system, it can result in a significant benefits for the user as well as the improvement in the CT scanning result, if the CT devices is used in the most efficient manner possible. Each source and measurement mode has its own advantages and disadvantages that must be considered in relation to the task and workpiece under investigation. By using the 225 kV microfocus tube will resulting in a better resolution, and as a result, the ability to recognize the sample are more detailed and sharp. It is generally agreed that using the 450 kV tubes will resulting in lower CT artifacts but better result in dimensional measurements, especially if you are not particularly concerned with fine geometries. When a part is made up of both metallic and polymeric components, the CT results obtained with the high energy tube are usually better and can be more accurately evaluated than the results obtained with a 225 kV tube, for example.